Assalamu wabarakatuh and good morning to everyone. So today's topic will be on process management. This is a lecture number 5 for subject operating system, and this is second session of recording lecture. Okay, the process is a self-explanatory, the job that you need to do and to complete. So the analogy is the first one is the staircase at a building was built as a fire escape. So if you go to the large building, tall building like apartments and tall building. Okay, it's just like the staircase at the building, like apartment or tall building, as they were built as a fire escape route. But people in the building often take the stairs instead of the slow lift. So yeah, it's always good to take the stairs because this is more healthy and more environmental friendly. Uh, the stair is only wide enough for one person. So we're talking about very small stairs. You only just good enough for one person, which is in reality is not really true. It's a big one. You can at least two normal person, or three small person that can use the stairs at the same time. And the traffic flows smoothly unless there are two people moving in opposite directions. So you have a standoff on that. So there's a landing between each floor that is wide enough for people to share. And a problem occurs when someone going up the stairs meets someone coming down and each refuse to retreat to the landing, thus create a deadlock. So you have these stairs, and this is one person and this is another person. So you have a standoff, and this is called because this person 1 and person 2, person 1 cannot go down, person 2 cannot go up. So in this case you have a deadlock. We name it as a deadlock. Another possibility, a few patient people wait on the landing for a break in the opposing traffic, and the break never comes. They could wait forever. So this is called a starvation. So you have a deadlock where it's stuck here. Person number 1 cannot go down and person number 2 cannot go up because this is just enough for one person. Another one is starvation. This in a like traffic jam in on the road where they're waiting for the break, but the breaks actually never came or very late. So this is called starvation. Deadlock and starvation. A lack of process synchronization may lead to deadlock. So you know what is a deadlock. So this is the like nicer term, a situation where the resources needed by a job to finish execution are held by another job, which in turn is waiting for other resources to become available. So the other name for the deadlock is deadly embrace, and we call it. And then another one is starvation. Totally, stuck. You cannot go anywhere. The result of conservative allocation of resources in which a job is prevented from executing because it is kept waiting for resources that never become available. So the meaning of conservative is so this in a traditional way. It's not dynamic, it's not flexible. You have to wait for this process to finish before I can give you a path, or you can before I can release you, or I can give you a pass. So this is a conservative mean, a traditional way, not dynamic. Only one rules. There's no other rules. It's not flexible. So a deadlock effect affects more than one job. Example of deadlock is traffic jam. Only outside intervention can resolve a deadlock. So what is outside intervention? So you have to go for police traffic to block another to block one route and to allow another route. Deadlocks are prevalent in interactive system because the system is more flexible than the batch environment. So the batch environment is like a serial one by one von Neumann architecture, a typical serial only one flow, only one job at time. So in these multi-processors, multi-core computers nowadays, deadlocks are more prevalent because the process are more dynamic where you can run much more processes or jobs at one time compared to the traditional von Neumann architecture. Interactive systems improve the use of resources through dynamic sharing, but this also increases the possibility of deadlocks. So you have an interactive system or dynamic. It does improve in a way. It does improve in a way to to minimize deadlock, but still it also can increase the possibility of deadlocks. So this is a situation of a traffic jam where because there is no no one giving a chance, no one giving or no one's want to release the traffic. So this is a kind of situation of deadlock, a typical or normal situation of deadlock in a traffic jam system. So it usually occurs when a non-shareable, non-preemptible resources like files or printers are allocated to jobs that eventually require other non-shareable, non-preemptive resources that have been locked by other jobs. Meaning that, okay, let's say you have two computers, you have two computers, you have two computers that want to for a printer. Let's say this one send a job here, this computer one send a job for instruct a printer to print to print a document, but the printer somehow they have a bugs, cannot resolve this, cannot complete the job. So computer number two when send instruction, the computer number two will not be able to print his document because of computer number one never released the jobs, never released a requested to the printer. So there are 7 cases of deadlocks. Deadlocks on file requests, databases, dedicated device allocation, multiple device allocation, spooling, and disk sharing. We will go one by one in all these 7 cases of deadlocks. Okay, the first one is deadlock on file requests. Occurs when jobs are allowed to request and hold file for the duration of their execution. So if you want to access a file, meaning that that slot is dedicated to you, so no one can ever access the file before you complete whatever task you've been given for that files. Example, a home construction company has two departments, purchasing P1 and sales P2. Both departments need access to two files, which is inventory files F1 and suppliers file F2 to update daily transaction. So a deadlock occurs when the following sequence or event takes place. Purchasing P1 access the supplier file F2 to place an order for more lumber. So purchasing P1 access the supplier file F2 to place an order for more lumber. So you have here, okay, purchasing P1 access the supplier file F2. So he requests and this one allocated to P1. And then sales P2 access the inventory file F1. Okay, you have here P2 access the inventory file F1. So you have a request and this one is allocated, this one a request and this one is allocated. So now F2 is allocated to P1 and F1 is allocated to P2. P1 doesn't release F2 but requests F1 to verify the quantity of lumber. Okay, while P1 being allocated A2, P1 also tried to access the F1 to verify the quantity of lumber on hand before placing an order, but P1 is blocked because now it is blocked. Sorry for that. It is blocked because now F1 is serving P2 and P2 haven't yet released F1. Uh, and P2 at the same time request for F2 to check the subcontractor's schedule. So request the F2. So make a request here. So you have a request block for P1 to F1 and P2 request for F2, but it is also blocked due to F2 is now serving P1 and P1 never released F2. So this is one typical situation of deadlocks in a file request. So at the moment F2 is serving P1 and F1 is serving P2. At the same time, P1 tried to access F1, but it's blocked because F1 now is serving F2. And at the same time, P2 tried to access F2, but F2 cannot allocate a request to P2 because now it's serving P1. So you have here, this is a nicer. Okay, you have purchasing P1, requested suppliers F2 and is allocated. So now suppliers file F2 is serving P1 and same for inventory F1 sales requested and this one is allocated. So sorry, this is the wrong arrow. So this is the real arrow. Ignore this. So request and allocated. At the same time, P1 tried to access F1, but since F1 sales because F1 is serving P2, so this is blocked. P1 cannot access F1 at the same time P2 cannot access F2 because F2 now is serving P1, so the request is blocked. And any other departments that require F1, any other departments like the engineering departments or whatever accounting departments that requires F1 and F2, let's say you have a P3 for engineering and P4 for accounting. If they want to access any of this file, it also will be blocked. This one will be blocked because now supplier F2 is serving the F2 file is serving P1 and the inventory is serving P2. The deadlock will remain. This will block this 1, 2, 3, 4 will be 1, 2, 3 and 4. The deadlock will remain until one of the program is withdrawn. Okay, let's say P1. Okay, never mind. I don't want to access anymore. I want to take a break. Or it is forcibly removed and it's file release. So you just control and delete, you end task, something like that. Only then can the other program continue on and the system returns to a normal state. Occurs if two processes access and log records in a database. This is deadlock in databases. Two processes and log records in database. Similar with the file cases deadlocks in accessing the files. Locking is a technique used to guarantee data integrity by locking out other users while working with the database. So let's say if these users accessing this database, that section is locked for him. That database's file is locked for him. No other users can access that database until he completed or he released the accessing the database. Locking can be done at 3 levels. The first one is lock the entire database for the duration of the request. So you set a timer. Log a subsection of the DB. So okay, I give you this. This is the whole database. I give you one subsection for you to access first. This will be locked for you only, but others are open. And lock individual record. So this is individual database accessing. Locking increases the possibility of deadlocks. Okay. Examples: a system locks a record when it is accessed until the process is complete. Two processes P1 and P2 need to update two records R1 and R2. So you have a P1, you have two processes P1, refer to the process P1 and P2 need to update two records R1 and R2 when it's accessed until the process goes. So if like P1 access R1, this is locked. So let's say P2 want to access R1, it will be blocked. Same with P2 now is accessing R2, so it is locked. And if P1 try to access R2, it will be blocked. So this is a deadlock in databases. The following sequence leads to a deadlock. P1 access R1 and locks it. P2 access R2 and locks it. Same as okay. P1 and P2, R1 and R2. So P1 access R1 lock. P2 access R2 and lock. P1 request R2 which is locked by P2. So P1 try to request R2. Request. But now R2 is serving P2, so this is block. And same, P2 is try to access the R1. But now R1 is locked with process 1. So this one P2 will also be blocked. Alternative, do not use locks, but this may lead to integrity problem. The updated record might include only some of the data. This is known as a race condition. So if we talking about the race condition, the updated records might include only the same of the, this is known as a race. So if we talking about the race condition, let's say you have an initial value. Okay, let's say you have an initial value of x is equal to 10. Okay, this is the variable that, okay, you have a two processes, process 1 and process 2, and you want to access this. You want to access this is the typical race condition. So x, so now x equal to x plus 10, and the new this will be a new value of x, and this one also x plus 10, and this is the new. So let's say we go for P1 first. P1 access the variable. So P1 access the variable x, and it will record x is equal to 10. And P2 access, after P1 access the x, release, and then P2 access x, and x is also equal to 10 from P1, and this one from P2. So now the second instruction, x equal to 10. So x will become x, 10 plus 10 is 20. So this is P1. P2 will be x plus 10. So the new value of x will be 20. But P2, when P2 access the x, P2 still assume that x is 10, and x 10 plus 10 is equal to 10 plus 10 is 20, which is P2, which this is totally wrong. The correct answer will be x equal to 30, because when P1 increment to 20 and P2 increment to 10, so it will become 30. This is the correct answer. But P2 no, because it can swap and never updated in the memory, so P2 can P2 still assume the value of x is 10, and it will increment itself. 10 plus 10 is 20. So this is the wrong answer. So this is what I mean by the race condition. Sorry for that. Just bear with me. So alternate do not use logs, but this may lead to integrity problem. So if you see examples from your slide, okay, you have a child, these shared variables or shared records, and P1 grade process and P2 read process data. So it's grade process and reads data, meaning that only grade process, other data remains intact. It only process grade. So you updated the grade 3, and others remains unintact, child and address college 12. And this one P2 process is it will address process, it will update the address, and others remain unintact. So this one you have child, the grade is still 2.5, but the address changed to section 17. So when P1 try to rewrite its record to DB with new GPA, so child have a 3.0 GPA 3.0 and code is 12. But from process 2, Chow GPA is 2.5 and section 17. So this is two different value for Chow. Two different condition for Chow. This is involve integrity problem. Integrity problem. If you allow only some of the data, this is known as a race. Okay. So let's say P1 only have P1 only P1 only can access grade or can change update, so GPA 3.0, and P2 only can update address, others remain unintact. So address is changed here, and this one grade is changed here. So you have here two different values, which this is the integrity problem, which is not true. Okay. Okay, deadlocks in dedicated device allocation. Two users run two programs, P1 and P2, and both programs needs two tape drives to copy files from one tape to another. So two tape drive is like solid state drive or hard disk drive. The following sequence leads to deadlocks. P1 requests tape drive 1 and gets it. P2 requests tape drive 2 and gets it. P1 requests tape drive 2 but it's blocked. P2 requests tape. So just like P1 and P2. So tape drive, sorry. So tape drive is tape drive 1, tape drive 2. So P1 request and T1 allocated, P2 request and T2 allocated. Okay, and then if P1 try to request it, it is blocked because now it's serving P2. And if P2 try to access to request T1, it is also blocked because now it's serving P1. This is blocked. Okay, P1 request. Neither job can continue because each waiting for the others to finish. They are selfish. No, I will not stand down. You have to finish. You have to release first, not me. And the other party just said, no, you. It's supposed to be you. So they are selfish, and they no, it's a deadlock situation. So dedicated device, so it said now it's a multiple device allocation occurs when several process request and hold on to dedicated devices while other process act similarly. None of the jobs can continue because each is waiting for resource held by another. So you have when several processes P1, P2, P3 request and hold on to the dedicated devices while other processes act similarly. So none of jobs can continue because each is waiting for resource held by another. Okay, now you have this is a situation. This is a situation of deadlock in multiple device. So you have a tape drive. You have a okay. This is a process one. It requested to use a tape drive, and now the tape drive is allocated or serving P1. And then now okay, process 2 request for printer, and now printer is allocated job to P2. And this one P3 is P3 requested a plotter, and it is allocated to P3. So let's say if P3 try to access tape drive, if P3 try to access tape drive, but now tape drive is serving P1, so this will be blocked. And let's say P2 try to access the plotter, P2 try to access the plotter, but now plotter is serving P3, so the request is blocked. Same goes for P1. P1 try to access a printer, but printer is now serving P2. Unless it is finished, the request will be blocked. So this is the deadlock situation in multiple device allocation. And then deadlocks in spooling. New one. So although a printer is a dedicated device, it can be transformed into shareable device by installing a disk between it and the CPU. So you have this is your PC, and this is the this is the a virtual disk, and this is your what call a printer. Sorry, not good at this is a printer. Better to label. Okay, this is the printer. So any instruction or any command will go to the virtual disk first. So virtual disk will list print 1 what, print X, 2 print Y, print 3 print 3 print Z, and so on. So it is parked on virtual disk first. It's like a catch. The disk accepts output from several users and acts as a temporary storage area for all output until the printer is ready to accept it. This is known as a spooling. This is a spooling. Okay, the job. Temporary storage area, virtual disk for all output until the printer is ready to accept. This is called a spooling. If the printer needs all of jobs output before it begins printing, but the spooling system fills the available disk space with only partially completed output, a deadlock occurs. So printer needs to need all of jobs output before it begins printing, but the spooling system fills the available disk space with only partially completed output, a deadlock occurs. So you know the virtual disk also has some limited space. If it's full with all this spooling without any completed job, the printer cannot print because printer only print a completed job, a completed output. Okay, so this is scenario 1 hour before an important project deadline. Members of your teams are frantically finishing the details. This provided you all do the works together. Okay, no one is like lazy enough, just depends on others. A few minutes before the deadline, all team members issue the print command. The spooler receives the pages one at a time, but the pages are received separately, page 1, page 2, and so on. So the spooler receives the page 1 at a time, but the pages are received separately, page 1, page 2, and so on. This only a pages, but never a completed job, never a completed print. So the printer is ready to print, so you have multiple, sorry, I don't know why it become this one. So you have here P1, P2, P3, P4 sent to the temporary storage. Okay, and temporary storage has page 1, 2, page 3, page 10, and so on. The printer is ready to print the first completed, but as the spooler canvas is file, it has the first page for several documents, but none of the completed document. So in order for printer to print, it must print a completed job, not a partial job. Since the printer only accepts completed files, none of the documents can be printed, because now the spool only gets like pages only. A partial completed job. No, the term is not correct. A partial jobs, not a completed jobs. Okay, so the printer doesn't accept that. Okay, you say to the temporary storage, sorry, I just want to print a completed jobs, not a partial one. So this is a deadlock situation in a spooling. So these are designed to be shared, not uncommon for two processes to access different areas of a disk. So deadlock in disk sharing. So remember, this has a sector and stuff. This ability to share creates an active type of deadlock termed live lock. Live lock. So process use a form of busy waiting that is different from a natural wait. It is waiting to share a resource but never gains control of it. So live lock is like, we go back to the situation of stairs. Okay, you have this one. This wants to go at that direction, going down, and this one wants going up. Actually, both of them can, if one move to the other side and one move to the other sides, the other one can go pass through, and same as the one that go to the other side. But it remains like this live lock. Okay, please give me when they have a miscommunication, both of them move to this part, to this area at the same time. So again, live lock, and then they move back to here because the instruction is not really clear. So this is like the live lock situation. Okay, they have this one, but both move to these sides. Still no one can go pass through, so again they move to the dead side at the same time. So this is called what? This is the simplest example of the live lock. Processor use a form of busy waiting that is different from a natural and wait. It is waiting to share a resource but never gains control of it. Okay, so the example, a system that performs daily transaction at insurance company. P1s, okay, this P1s wants to show a payment and issues a command to read the balance, which is stored in cylinder 20 of the disk. So P1 issues a command and input output. So input output, and this control unit try to find the location for cylinder 20. Okay, while the disk control unit is moving the arm to cylinder 20, P1 is put on hold. Okay, now P1 is put on hold. So this one is process number 1. This is process number 2, hold. And the input output channel is free to process the net request. So input output channel now is release. 3, release. And now P2 gains control input output channel and issues a command to write another record. So issues a command number 4. Go to the disk control unit, and it try to locate the cylinder 310. Okay, try to 310. So while it tried to locate the P310, P2 is put on hold while the control unit move the arm to cylinder 310. But now P1 wants to access, P1 has, because this input output channel have been released, 6 release, okay, release P1, release P2. So now P1 is free, P1 access back and try to locate the cylinder 20 again. So number 7. So try to allocate the cylinder 20 again. And then same process happen because this one is allocate, so the P1 will put on hold and the input output channel is released and P2 will access again and the cylinder will try to find 310. As a result, the arm is constantly moving back and forth between cylinder 20 and cylinder 310 as it responds to two completing commands but satisfies neither. So now partial jobs. So all 6 deadlocks involve the interaction of several processes and resources. Each deadlock is preceded by the simultaneous occurrence of 4 conditions that the OS could recognize. The first one is a mutual exclusion, the act of allowing only one person's process to have access to the stairs. First condition for the deadlock. Okay, and then resource holding, when two people meet on the stairs, and each one hold grounds and wait for other to retreat. This is a second condition for deadlock. No preemption. Each step is dedicated to the climber or descender and is allocated to the holder for as long as needed. This lack of temporary reallocation of resources is the third condition for a deadlock. And circular wait. Each person involved in the impasse is waiting for another to voluntarily release the step, so that at least one will be able to continue and eventually arrive at the destination, a circular wait. So all these 4 conditions are required for the deadlock to occur as long as 4 conditions are present and the deadlock continues. Okay. So modeling a deadlocks. Now you have 4 conditions can be modeled using directed graph. Okay. I don't know whether you learned the graph. Directed graph mean one way, and directed graph meaning that R1s want to go to the P1 one way. So you put an arrow here. So this is a graph, if you learn from the graph theory, which I will talk about, just briefly explain to you. If R1 wants to go to the P1, it's only one way. So this is a directed graph. You put an arrow. P1 is holding R1. So P1 is holding R1. Meaning that R1 is serving P1. R1 serving P1. And let's say P1 is waiting for R1. This one, P1 request for R1. So P is process, P process, and R is resource. Can be printer, can be files, can be anything. Okay. A cycle in the graph means there is a deadlock. Okay. Let's say R1 now is serving P1. R1 now is serving P1, But at the same time, P2 try to access R1. So this is a block condition. Block condition. At the same time, R2 is serving P2. P1 try to access R2, it is blocked. So a cycle in the graph means there is a deadlock. Assume a system has 3 processes, P1, P2, P3, and 3 resources, R1 printer, R2 disk drive, and RT is a plotter. This is a multiple device deadlock. So you have event 1, P1 request, and is so you have event P1 request and is allocated printer R1. So P1 R1 request and allocated printer R1. So R1 is serving P1. R1 is serving P1. Serving. This is request. So you don't have request. P1 request R1, R1 is free and is serving P1, so we don't need to show the request. P1 release R1, so P1 release R1, so this is the first, and the second will be P1 release R1. So when P1 done with the job on resources 1, so P1 will release R1, so no more, it's not serving, R1 is free. R1 is free. P2 request and is allocated this R2, so P2 R2, so R2 is serving P2, serving P2 release R2, so number 4 is P2 and R2. Sorry for that, we don't have much space, so 4 P2 and R2. Since P2 done with the R2, so R2 is free now, release. P3 request allocated plotters R3, P3, so number 5 is P3 and R3, so R3 is serving P3, R3 is serving P3, and P3 request for, and the 6 is after R3 done, P3 done with the R3, so P3 will release R3 and R3 will be free again. This is scenario 1. So the first one, P1, okay, P1 request for R1, R1 is free, so now R1 serving P1, and then after P1 done with the R1, P1 will release R1, so R1 is free. Then P2 request, so this one is request, this put area request, and this one is serving P2. Sorry for my bad handwriting. Serving P2, and after P2 done with the R2, P2 will release R2. And this one is like P3 request, and R3 is serving P3. And after they are done, P3 will request R3. So this is a situation where no deadlock occurs, ideal situation. There are no cycles in a directed graph. Conclusion, a deadlock can occur even if each process requests every resources. If the resources are released before the next process request them. If the resources are released before the next request process them. Let's say now P2 is R2 is serving P2. If process 1 try to request R2, this will be a block condition. So modeling deadlocks. Scenario 2. Okay, we can, don't know why. P1 request and is allocated R1. So this one P1 and R1. So R1 now is serving P1. And P2 request in allocated R2. So R2 is serving P2. R2 is serving P2. P3 request and is allocated R3. So R3 is serving P3. Sorry, yeah, P3. P1 request R2. So we have P1 here, we have P2. We have R1 and R2. Now R1 is serving P1, R2 is serving P2, but P1 here try to request R2. So this is a block condition. P2 request R3. So if you have here now P2 now P2 and P3. So P2 R2 is serving P2, R3 is serving P3. P2 request for R3. Now this is the block condition. And P3 request R1. So we look at R1 here. R1 is serving P1 and P3 is serving R3. And P3 request R1. So this is the block condition. Okay, this is a modeling deadlocks. Okay, you have here. So this is the P1 request. R1 is serving this is serving, and this is serving. So you have a block condition when R2 is serving P2, P1 try to access R2, this is block. Same, R3 is serving P3, this is block. P2 cannot, R3 cannot serve P2, so block. So same one, R1 is serving P1, but at the same time P3 try to access R1, this is also block. There's a deadlock. Okay, scenario 3. P1 requests and is allocated R1. P1, R1, R1 serving P1. P1 requests and is allocated R2. So P1, R1, and R2 both serving P1. P2 requests R1. So you have here P2. Try to request. You have P1, P2. You have R1, R2. Both now is serving P1. And P2 try to request R1. So this will be blocked. And then P3 requests and is allocated R3. P3 and R3 request. So R3 is serving P3. P1 release R1 which is allocated to P2. So you go back here. P1 release R1 is allocated to P2. So P1, R1, and R2 and P2. So last time R1 is serving P1 and R2 is serving P1. P2 try to request R1. But since R1 now is released, so now R1 will be serving P2. P3 request R2. So P3 try to request R2, but now it's still blocked because R2 is serving P1. P1 release R2, which is allocated to P3. So when R2, P1 done with the R2, so this one is not serving, R2 will be free. And R2 now, instead of blocking, now will serve P3 in this case. Because R2 already released, P1 done with R2, and R2 will be released to R2 will be serving P3. So there is no more block conditions for this process 7. So you can see here, okay, P1, this the typical P1, R1 and R2 serving P1. So when P2 try to access R1, cannot because it is blocked. And RT is serving P3. This and then when R1 is done with P1, so P1 will release R1, release. P1 release. Release R1. So now P2, R1 will be serving P2. So the first condition block when P1 is released. So now R1 can serving P2. And P3 also release R3. So now when P3 release release R3, yes. Okay, P3 request P1. P3 request R2. P3 request R3, yes, correct. P3 never release. Actually, P3 never release R3. This is quite confusing, but never mind. So RT never release P3. Just don't want to make you confused. We will go for. So this is a normal conditions, okay. There's a mistake in the slide, but never mind. So R3, P3 never release R3. uh, but P3 requests R2. So when P3 requests R2, so P3 requests R2, which is now blocked. Okay, blocked because R2 is serving P1. Then that one P1 when P1 already so this R2 is serving P1. When P1 done with R2, it will release P1 release R2. Now R2 is free to serve P3. Before this a block condition. Now R2 is free to serving P3. So you understand? Just go back to this scenario and try to draw yourself, which is easy when you get it. Okay. The graph can be expanded to include several resources of the same type that can be allocated individually or in groups to the same process. Devices of this same type are clustered into one entity. The arrows show the links between a single resource and the process using it. So what I mean that the graph is meant to include several resources. Devices of the same type are clustered into one entity. So we have device included in one entity. The arrow shows the links between a single resource and the process using it. The arrow shows the link between a single resource and the process using it. So this is the resources. Same resources is types are clustered into one entity. So this is the resources clustered into one entity. So now the serving P1, serving P2, and serving P3. So A is a stable condition when all three processes request one more resource without reaching the one they are using. A deadlock occurs as shown in B. Okay, B is a deadlock. Okay. Now P1, P2, and P3. When P1 try to request and P2 also try to request, so this will is a deadlock situation. So strategies for handling deadlocks. Request and release are unpredictable and that make it difficult to design a foolproof preventive policy. So if in the dynamic case, it's really unpredictable. You cannot really predict what is the future process, which one they want to access the file and so on. Every day a different task, a different process, access the different files. Unless you gather a data for 1 year, it's really difficult to do to predict what they want to access in future. Three strategies to deal with the deadlocks is prevention. Prevent one of the four conditions from occurring. The mutual exclusion, the preemptive, the circle. Avoidance. Avoid the deadlock if it becomes probable. And detection. Detect the deadlock when it occurs and recover from it gracefully. So we're going to see all these three strategies. Prevention. The OS must eliminate one of the four necessary conditions to prevent a deadlock complicated. The first one is mutual exclusion. It's necessary because certain resources must be exclusively allocated to one user at a time. Remember our example of x equal to 10. So this is process 1, x uh, x equal to x plus 10 and x, final value x, and P2 also, and you have x, you have x, you have P2, and you have x, and you have x plus 10, and you have x here. So remember mutual exclusion when you lock exclusively allocated to one user at a time. So if you, okay, in this order, P1 must complete first before P2 can take charge. So the last value of X is 20 for P1, and then it will go to P2. So P2 will have 20 plus 10 is X equal to 30. So you can get the correct value. So this is mutual exclusion. Exclusively, certain resources must be exclusively allocated to one user at a time. So let's say we P1, when P1 is accessing the X10, P2 cannot access X10. It is a mutual exclusion. P2 must wait until P1 process complete first, and then P2 gonna use that the final value, and P2 gonna increment the X. Resource holding can be avoided by forcing each job to request every resource. It will need to run to completion when it starts executing. But this approach only works well in batch environment. Batch environment, remember the von Neumann architecture, the serial one by one, but it's not suitable for interactive or dynamic system. Prevention 2, no preemption could be bypassed by allowing the OS to deallocate resource from jobs. No preemption could be bypassed by allowing the OS to deallocate resources from jobs, okay? And circular wait can be bypassed, no preemption could be bypassed by allowing the OS to deallocate resource from jobs, so that if the jobs take too long, you can bypass that. And circular wait can be bypassed if the OS prevents the formation of a circle. So the solution is based on a numbering system for resources: printer number 1, these two, tape 3, and plotter number 4. Whereas the formation of a circle. Solution is based on numbering system. So you have printer is resource 1, these two resource 2, tape 3, and plotter 4. And job must request for its resources in ascending order. So printer must come first, this second, tape 3, and plotter number 4. If a job needs a printer and a plotter, let's say job needs a printer and a plotter, it will request for a printer first. Job need a printer and a plotter, so it will go to printer first, then a plotter. Even if the job needs to use the plotter first followed by a printer, let's say it request for plotter and first, and then it request for the printer, it will still select printer first, request for printer first, and use it later. A job has to anticipate the order in which it will request for resources. So everything must be in order, ascending order. So we go for the avoidance. The OS can avoid a deadlock if it is known in advance the sequence of requests associated with each active process. The banker's algorithm proposed by Dijkstra regulate resource allocation to avoid deadlocks. So Dijkstra have this banker's algorithm. Dijkstra is a very famous physician. Last time there are no programmers. All programmers are called physicians. This is 1960s, 70s. So these are actually quite good programmers, or at that time physicist, sorry, not physician. Physician is a doctor. Physicist. Okay. The algo is based on bank with a fixed amount of capital that operates on the following principles. No customer will be granted a loan exceeding the bank total capital. Okay, this makes sense. No customer will be granted a loan. So like customer wants to loan 30,000, but the bank only have 20,000, so customer will be that customer will not be granted 30,000 because bank only have 20,000. So you have to accept 20,000, not 30,000. All customers will be given a maximum credit limit when opening an account. No customer will be allowed to borrow over the limit. So you have been, okay, this customer A, your borrow limit is 5,000. So if he tries to borrow 10,000, it will not be allowed. The sum of all loans won't exceed the bank's total capital. So sum of all loans will not exceed the total capital. So like customer A, B, C, the total amount is 20,000, and the bank has 30,000, so the bank can loans all this customer A, B, C. So we see the avoidance here. Customer C1 Okay, total loan 6,000, 2 and 4 loan amount. Maximum credit 4,000. Total capital fund is 10,000. So the bank still have 4,000. The bank is in a safe state because if looks at the remaining credit here, 4,000, the bank can serve customer 1, pass, customer 2, banks have 4,000 and remaining 3,000, yes, pass. And C3 also, bank have 4,000 and C3 remaining credit is 4,000. So the bank can serve all this. You look into the individual requirement, not total. So if this 4,000 and the banks can serve the remaining credit, the bank is in a safe state. Okay. So let's say a few weeks later, some loans have been repaid and more loans are made. The bank is unsafe state. So, few weeks later, some loans have been repaid and more loans are made. The bank is unsafe state. Okay, because only 1,000 left and the bank cannot satisfy anyone maximum request. So now total loan is 2,000, 3,000 and 4,000. So total loan is 9,000, total capital fund is 10,000, so the bank only left 1,000. If we go for the individual requirements C1, C2 and C3, so we have here 1,000, remaining credit 2,000, 2,000, 4,000. So the bank is said it is said in an unsafe state because the bank cannot serve the remaining credit of each customer. Okay. An unsafe state does not necessarily lead to a deadlock, but is an excellent candidate for one. So this not necessarily translate to the deadlock, but is an excellent candidate for one. The customers are not required to request for maximum loan, but the bank doesn't know the exact amount that will be eventually requested. And as long as the bank capital is less than the maximum amount available for individual loans, it can guarantee that it will be able to fill every loan request. Okay, if it is if the capital is less than the maximum amount available for individual loans, it cannot guarantee that it will be able to fill every one request. So at most it can serve only 1,000 because this is a remaining capital fund. So you have job number 1, 2 and 3. This is another example. Total number of devices allocated is 6. 2, 1, 4, 6. Total number of devices in the system is 10. So you have 4 remaining. This is a safe state. 6 devices allocated, 4 are still available. So if customer number 1, 4, you still can the job still can process because job number 1, sorry, the total jobs, because they have still 4 device allocated for, and this one also pass and this one also. So this is a safe state. Using the resources released by the finished jobs, the maximum needs of another jobs can be filled and that job can finish, and so on until our jobs terminate successfully. So this is a safe state because remaining 4 can serve each customer. Go into the each customer, not the total remaining needs. So let's say you have total number of device located is 9 and total number of device in the system is 10. So 10, you have 1. You have 1. And then if you see remaining needs, customer number 1 you cannot serve, customer number 2 you cannot serve. So this is unsafe state. This is an unsafe state, just like the bank example just now. So the OS must be sure never to satisfy a request that move it from a safe state to an unsafe state. The OS must sure it never to satisfy a request that move it from a safe state to an unsafe state. When a request is received, the OS must identify the job with the smallest number of remaining resources and make sure that the number of available resources is at least equal to the number needed for this job to run to completion. Okay, so when a request receives, the OS must identify the job with the smallest number of remaining resources and make sure that the number of available resources is at least equal to the number of needed for this job to run the completion. So let's say this is a OS, so it must make sure like the number of the device resources to allocate remaining needs at least a minimum number 3 or maximum number 4, so it can allocate each job or each customer resources. The banker's algo is not always a practical because as a job enters the system, it must predict the maximum number of resources it needs. Not practical for interactive systems. So it's very difficult to predict. You can do whatever model, but it's never gonna be accurate. Your prediction also can be wrong. The number of total resources must remain constant. If a device breaks, the algo won't work. So number of resources, like, okay, assume that all devices of all computers or all hard disks is in their normal state, functioning state. If one doesn't function, the algo won't work. The algo will be break. The number of jobs must remain fixed, not possible in interactive system. So number of jobs in the normal interactive system is dynamic. It, it will never be a fixed one. It based on the user's requirement or the process requirement. So the overhead costs of running the avoidance algo can be quite high when there are many active jobs and many devices because it has to be invoked for each request. So when there is many active jobs and many devices, it will it need to be invoked for each request. Resources are not well utilized because the algo assume the worst case. Hence, keeps vital resources unavailable to avoid unsafe states. Resources are not well utilized because the algo assume the worst case. Hence, keeps vital resources unavailable to avoid unsafe states. So it always assume the worst case. Scheduling suffers due to poor utilization and jobs are kept waiting for resource allocation. So you try to schedule, but the utilization of your scheduling is very poor because jobs are keep waiting for resource allocation. May lead to indefinite postponement of a more complex job requiring many resources, so it will be a deadlock. So now we go for detection. Deadlocks can be detected by building directed resource graph and looking for cycles. Okay, directed graph. The detection algo can be executed when appropriate, like every hour, once a day, when there is no noticeable throughput degradation. The detecting algo reduce a directed graph. Steps to reduce a graph. Find a process that is currently using a resource and not waiting for one. Remove the process from the graph by disconnecting the link tying the resource to the process. The resource is returned to the available list. So find a process currently using a resource and not waiting for one. Remove the process from the graph by disconnecting the link. Okay, we go for this example later. So number 2, find a process that is waiting for resource classes that are not fully allocated. Process waiting for resource classes that are not fully allocated. This process does not contribute to deadlock since it will eventually get the resource it's waiting for, finishes and return the resource to the available list. Go back to step 1, and process number 3 is go back to step 1 and continue with the steps 1 and 2 until all lines connecting resources to processes have been removed. So you have here in A, P3 is currently using a resources and using a resource and not waiting for one. We can remove this process from the graph, thus rating P3 is currently using resource and not waiting for one. We can remove the process from the graph, thus So P3 before this is using the R3, serving RT is using P3. P3 is not waiting for anyone, not requesting other resources. So we can remove this process from the graph, thus releasing R3, which can be allocated to P2. So you can to the P2, which can be allocated, resulting in B. Sorry, this is B. Oh, sorry, okay. In A, okay, P3 is currently using resources and not waiting for one. You can remove this, and thus releasing R3, which can be allocated to P2. P2 requests R3, but now P2 requests R3 previously, but it cannot use R3 because R3 is serving P3. So now when P3 finish using R3, you remove the directed graph here, then R3 will serving P2, which is a B. The link between P2 R3, the link between P2 R3, P2 R3 and P2 R2, P2 R2 can be removed because P2 has all of its requested resources and can run to completion, resulting in C. So you can remove these two, this B, and you can remove because R2 and R3 waiting for completion. So when finished, R2 and R3 can be released. So it will become diagram C. The resource released by P2 is allocated to P1. So previously P1 is requesting R2, but R2 cannot serve P1 because R2 is serving P2. So when it has been released, so R2 is serving P1 and R1 is serving P1. So the links between P1 R2, P1 R2 and P1 R1 can be removed because P1 has all request resources and can finish successfully. So when when R1 and R2 finish serving P1, the graph will be released and this back to the normal state on D. If there are any lines left, this indicates that the request of the process cannot be satisfied and that a deadlock exists. So if any of the lines left, if any of the lines left, if any of the lines is removed, so the deadlock will not be occurred. But if any lines left, this indicates that the request of the processes cannot be satisfied and that a deadlock exists. The following graph shows a deadlock situation. So in A, the links P3 and R3, okay, in A, the links P3 and R3 can be removed because P3 not waiting for resources. So R3 is serving P3, P2 is waiting for R3 to serve him. So you can remove P3. So when P2 requested R3, then R3 can serve P2, become B. In B, P2 only has 2 of 3 resources it needs. So P2 also requests for R1. Same time R2 and R3 is serving P2. So P2 only has 2 of 3 resources it needs and is waiting for P1 to release R1. So now R1 is serving P1. So P2 have to wait R1 finishing serving P1. P1 needs R2 and is waiting for, at the same time P1 needs R2, but R2 is serving P2 to release R2. So P1 is waiting for R2 to release, P1 is waiting for P2 to release R2 and P2 is waiting for P1 to release R1. The system deadlocks because both process, you see the deadlocks here, block, and this one also block, because P1 wants to access R2, but R2 serving P2, so it's blocked. P2 wants to access R1, but P1 is serving R1 is serving P1, so it is blocked. The system deadlocks because both processes are waiting for the other to release the resources it requires. So the system is in a deadlock situation. So recovery process, once a deadlock is detected, you have to recover. The best way is control alternate delete and task or whatsoever. It must be untangled and the system return to the normal as soon as possible. Recovery algorithm require at least one victim and expendable job. So one victim, unfortunately. Removing the victim from the deadlock will free the system. The job that becomes a victim has to be restarted from the beginning or from a convenient midpoint. So a victim, when it's removed, either it start from scratch or just at the point it being removed. So the method one is the simplest and most drastic approach is to terminate all active jobs and restart them. It's like restart your computer hang, you just restart the PC. It's easiest, but not very intelligent. But that is a basic troubleshooting. Basic troubleshooting is just on and off, reset, whatever. Method number two, terminate only jobs involved in a deadlock and ask the users to resubmit them. So like in case of P1, okay, P1, P2, R1, R2. So R1 serving R2 serving P2, P1 wants to access R2, and P2 wants to access R1. So terminate only jobs involved in the deadlock, so you can terminate all this. You can terminate this and the deadlock will not be occurred or deadlock being removed. Method 3, identify jobs involved in the deadlock and terminate them one at a time, checking to see if the deadlock is eliminated after each removal. So you check one by one all the process. Method 4 can only be used of the job keep Method 4 can only be used of the job if the job, if the job keeps a record or snapshot of its progress so it can be interrupted and then continue without restarting from the beginning. So if a process so it can be interrupted and then continue without restarting from the beginning. The snapshot is like the landing in the staircase. Instead of forcing ascender descenders to return to the bottom of the staircase, he only retreats to the nearest landing and wait for others to pass. So just one step behind. Let's say you have a stairs here. For somehow you have a space here. And this is you. And okay. He wants to go up and he wants to go down. So instead of forcing ascender to return to the bottom of the staircase, he only reaches the nearest landing point. You can nearest landing point. So you can remove here and this guy can move through. If you take the example of the staircase. He only reaches to the nearest landing and wait for others to pass. So if you move here, you are here now, so the guy can go pass through and you can resume your operation. So method 5 is selects a non-deadlock job, preempts the resources holding and allocates them to a deadlock process so it can resume execution, thus breaking the deadlock. And method 6 stops new jobs from entering the system to allow non-deadlock jobs to get the resources they need to run the completion. So just wants to add the previous four methods 1, 2, 3, and 4 deal with jobs caught in a deadlock. Method 5 and 6 concentrate on non-deadlock jobs on the resources they hold. So concentrated on non-deadlock jobs and resource they hold. Okay, non-deadlock job. So if you select a non-deadlock job, you see number 5, Stops a new job from entering the system to allow non-deadlocked jobs to get the resources they need to run the completion. So this is method 5 and 6. So there are several factors to consider when selecting a victim with at least negative effect on the system. Priority of job. High priority jobs are usually untouched. CPU time used by job. Jobs close to completion are left alone. So high priority jobs, the most important jobs are has a priority to be done first. CPU time used by jobs, so jobs close to completion are left alone. Don't I'm almost finished. Don't disturb me. Leave me. Just just allow me to complete the job. The number of other jobs that would be affected if this job was selected as the victim. Okay, so this is the factors you need to consider. Starvation. Starvation is the result of conservative allocation of resource where a single job is prevented from execution because it is keep waiting for resource that never become available. The dining philosopher's problem introduced by Dijkstra. Okay, this is the dining philosophers. This is a famous algo. Famous not algo. Famous problem description introduced by Dijkstra. This Dijkstra is a very very brilliant programmers. Lot of algorithm. And the famous theory of Dijkstra is of course the shortest path used in your Waze, Google Map, the simplest shortest path. So you have a starvation here, the philosophers. The philosophers three, okay, you have 1, 2, 3, 4, 5 philosophers. So P referring to philosophers. A sit round table, each deep in thought. In the center is a bowl of spaghetti that is accessible to everyone. Just assume this is like Chinese yam seng, yam seng or something when you eat together. There are forks between each philosophers 1, 2, 3, 4, 5 forks. The philosophers must use 2 forks on either side of the plate to eat the spaghetti. So if you need if each philosophers can only use 2 forks, not 1 fork. But there are only 5 forks, not 10, so that all can eat at the same time. A philosopher can only eat or drink at a given time, but cannot do both. P1 is the first to start eating. P1 first start eating, so it will take these forks using F1 and F5. And P3 does likewise. P3, so P2 cannot use because F1 being used by P1. So P3 use F2 and F3. Okay, so P4 and P5. P2, P4 and P5 cannot eat because they don't have a fork left. P2 decides to begin the meal, but and then P2 decides to begin but is unable to start because no fork. P2 must wait. So P2, P4 and P5 must wait. When P3 finish eating and puts down his fork to resume his pondering. So now P3 finish eating. Should F2 be allocated to P2 in the hope that P1 will finish eating soon and F1 will be available for P2 to start eating? If yes, the dinner could slip into unsafe state. So the resources are allocated to philosophers only when both forks are available at the same time. So P4 and P5 still thinking, even though the forks already P4 and P5 still thinking, and P1 hasn't finished eating. P3 decides to eat again, so it takes P2, F2, and F3. And then he's able to take F2 and F3 once again. Soon, therefore, P1 finish. So P1 finish. Soon P1 finish and release F1 and F5, but P2 is still not able because P2 still not able to eat because F2 is used by the P3. This scenario could continue forever and P2 ends up starving because resources required never released. So P2 can be starved because the resources required is never being released. Let's say P3 finish eating Same time, P1 start to eat again. So P2 is in high risk to be starved because it can never use the forks. So in a computer environment, the resources are like forks and the computing processes are like dining philosophers. If the resources manager does not watch for starving processes and jobs and plan for their completion, they could remain in the system forever. Never complete the jobs, never have a chance. Once a system is detected, the system can block new jobs until the jobs have been satisfied. So once system detected, the system can block new jobs until jobs have been satisfied. Okay. So you can use also the aging factor. So that's it for today. Thank you very much.